All right, we'll start the Rust meetup. Thank you, everybody. Thanks for coming. Yeah. So he will. How do you?
Gergo.
Gergo. He will do a sharing on the Rust on the AVR.
Yeah, and the most important thing about this is that I decided to do this today because I saw that whoever was going to talk to cancel. So this is not like a real talk, okay? It's not a talk, it's just me rambling. And also, this is like breaking news because this is a computer from, we'll get to why this is on screen, but this is from like the mid-70s. And the work that I'm going to be talking about involves this computer, and it involves work that I actually did in 2017, so everything is brand new, right? Okay, so this is a computer from the 70s, but I think it's a recreation of the computer, the Cosmac VIP, I think. It's a computer that basically no one knows. It was a very unsuccessful computer. It was sold in kit form. It had a weird 8-bit CPU, like not a 6502, not a Z80. In fact, this predates this. This predates the Intel 8080 even. But, and it has very little memory. And unlike what you see here, because here it has a keyboard, right? But the OG unit didn't even have a keyboard. It had a 4x4 keypad for you to type in machine code instructions. So then, and it had 4K of RAM.
When did you say they started selling?
Not about selling like it was a kit, so you order a kit and
Right.
then the 70s, like mid-70s. And so there was a small but enthusiastic community around it. And then the guy who designed the computer, basically, he wrote, so they had a magazine, or a design, right? It was all very unprofessional. And in design, he wrote a paper, or an article rather, because there's nothing scientific around it, but it was an article, and saying that to make good use of the 4K of RAM, and also to like just make programs smaller so that you can type them in more easily. Like this is an important consideration back then because you were just typing on the 4x4 keypad. He had the idea to make a higher level language so that you would load the interpreter for that language first, and then basically as a virtual machine, you would write your programs, and by programs I mean games, in the virtual machine language, right? And so this thing was called Chip 8. And nothing of this computer remains in the sense that the CPU had no lineage afterwards, right? It's not like how you can trace back the mother Intel CPUs all the way to the Intel 8086, right? It's not like how the 6502s in every computer in the 80s. No, this is a complete dead end. But the Chip 8 was so simple, so low resource, like it's such little resources to think about it, that and there was so many games that enthusiasts wrote because and so everything about this computer is super low specs. So you had 64 by 32 pixels with 1 bit per pixel, so each pixel either on or off. Right? So everyone was making games. It was easy to make games for this because all the assets were super easy to make, and the bar was super low. And then basically what happened is that Chip 8 became popular like several times. So originally when it came out, and then decades later, I think in the early or mid 90s, there was a resurgence because people realized that it's a really good target for learning how to write an emulator, right? Because it's well documented. It's not a real machine. Chip 8 was never a hardware. It was always just running as software. It's a virtual machine on these things. So it had lots of things that you don't need to worry about that you would have to worry about if you were emulating a real machine. And I think even to this day, if you look, go on the internet and look for like hints or like tutorials for how do I learn how to write an emulator, it always starts with, okay, the first thing you should do is write a Chip 8 emulator. And then I think it was like 10 years ago, roughly, like this is hand waving, but roughly 10 years ago, there was another resurgence because some guys started doing an annual Chip 8 game competition, right? And and of course it's fun because everyone is working with the exact same constraints that they had back in the 70s. But of course the tooling these days for for developing for it are much more advanced. Like people have written higher level languages that can plan to chip 8 and everything. But ultimately what you deliver could have been delivered on these same computers in the 70s. Okay, so this is just the background. So this is just so you know what a chip 8 is. And so 2017, I saw that LLVM and Rust in particular were getting AVR support. And so I thought, okay, well, I don't know Rust, but I'm curious. I think it sounds like a fun thing to try. So I had this idea because I kind of had the platform before I had the software. So like a year or so before this, I built this thing. So this is a crappy photo of a breadboard. And you can see on the breadboard there's something here, right? There's some blinking lights and some chip here. You have the unmistakable 4x4 keypad, bunch of wires, bunch of chips, and then you have an LCD here. So this is a microcontroller-based chip 8 implementation, which I basically just plugged together out of off-the-shelf components. So you can see that there's no PCB involved or anything. This is just me like just putting square pins into round holes, right? So this is something that I just found. Basically, okay, so this is what prompted this. So I was just browsing Simlim Tower and I saw this and I go, okay, I need to build a chip 8 machine because this is the perfect input peripheral for this. So that 4x4 keypad, right? It's not the 3x4 like you usually have like for telephones and stuff. This is hex. This is exactly what you need for a chip 8. And then this comes from some old Nokia telephone. Oh. It has 84 by 48 pixels, which is again almost a perfect match for 64 by 32. You just don't use a bit of the border, right? And okay, and so this is the heart of it. So this is a Adafruit Creamkit Pro something, but it's basically an AVR microcontroller. It's the same AVR microcontroller, the chip itself that you have on the Arduino. Surely you guys have heard of the Arduino. So this thing is up to 20 megahertz, 8-bit microcontroller. It has 2 kilobytes of RAM, but it has 32 kilobytes of flash. This is going to be important as we will see. And so how can it have different, what does it mean that it has just 2K of RAM but 32K of program memory? It's a hardware architecture microcontroller. So you have separate memory for code and separate memory for your program state. And so, So what you get when you buy this, right, is that this is the full thing. It's not just the chip. You can see that there are a bunch of other chips around it. And you can see this is the important part, the USB connector. So if you get this, just like a normal Arduino, you can plug it into USB to upload your programs onto it. It has an onboard clock at 12 megahertz. So even though the chip could run up to 20 megahertz, this only runs at 20. And you can solder, here you see these holes, but you can solder in headers into that. And the big thing it had, in contrast to Arduino for my need, is that it runs at 3 volts, not 5 volts. And that's important because, so the chip 8, like I said, had 4 kilobytes of RAM. The VM spec itself says that it has 4 kilobytes of RAM. This thing only has 2 kilobytes, but I found on some parts catalog some cheap serial RAM chip, like this one. So the photo is horrible, right? You can see that this is taken at night, whatever. But there is something here, you can see that. So this is a serial RAM chip, which means but it only supports 3 volts. That was the important thing. So if you connect this to this, you can use SPI, which is a serial communication protocol, to send bytes from here to here and then later on out them back. That's all it can do, right? So this thing has 2K of RAM. This thing is it's big because I think the smallest we get was 16K. So it's way overkill for our need. Okay, so you can offload the memory of the VM onto this thing, and that means that you only need memory for the state of the machine that you're running, but not for the emulation of the memory of the machine that you're emulating. Does that make sense? It's almost like if you use it as small, right? Except it's not done opportunistically, like swap usually is. It's just always used for, like, this is your memory as far as chip-8 is concerned. Okay, and then, because this does have 32K of flash, so you can store the 4K image that you want to run. The initial state you can store on this thing. So when you start it up, you can just send all the data here and then start the VM. This is important because, like, you can't put external, like, you couldn't upload your games into this guy, right? This is just a random chip on a board with a bunch of cables. But this one is a USB connector, so if you connect from your computer to this, and you upload your AVR program and it includes your games, that is a very convenient way of getting your games onto this chip, onto the memory chip. Okay, so I had this platform and I implemented chip-8 on this using C++. And so when I saw that Rust supposedly supports AVR, I thought, okay, that would be a fun project because Rust is a nice, somewhat higher level language, and this is a very small platform. This is super, it's slow, it doesn't have much memory, everything is like, this is, I mean, your washing machine has more powerful microcontrollers than this stuff. And I already had this thing assembled, so I didn't need to do any hardware tinkering, I just needed to make sure that I can upload some Rust program onto this thing. Okay, so this was 2017, and then there's like a long blog post I wrote back then. So it turned out that what they meant when they said that Rust supports AVR is that someone managed to compile a program that blinks a single LED and nothing else. It's a busy loop that blinks an LED. They were able to compile that using LLVM's experimentally backend and from Rust, and that worked. But nothing else did. So, okay, but this doesn't matter because this is all news, this is 2017, but the point is that there was lots of missing things, but I soldiered through. So what I did was, I made, and this is not the one, I made a cargo package, which, this doesn't show the function, so, which is no STD. So that means that this is a Rust library that doesn't use the standard library, because the standard library is big, and it uses a lot of language features, and so initial problem was that you couldn't compile that to AVR just because the compiler didn't work well enough. But the other problem is that you can accidentally pull in lots of crap that basically will just mean that you won't fit on your target size of. It's not 32K, right? You have less because you also need at least 4K to store your game. So yeah, so it's not STD library, but I wrote this deliberately before actually trying out the AVR backend of LLVM, because I wanted to write this as I would normally write some Rust program. Now, of course, I didn't know what that means because I was not a Rust programmer, but I thought, okay, but I'm going to at least write it in a natural style, using algebraic data types. So this is, for example, like all the chip-8 opcodes are defined, represented as some nice algebraic data type, and then you have the classic thing where you have a decoder function which takes in basically 2 bytes and then gives you the decoded opcode, right? And then you want to have a second function, which is the actual interpreter, which would be which basically would be this, right? Like if you want to run, well, this does a bit more now, but if you want to run, you fetch 2 bytes from the VM's memory, and then you decode it. That gives you the representation of the opcode, and then you switch on that, and then you do what that opcode does, right? Like you write this by just reading the chip-8 specification, and then you just bang out the lines, right? So I did it this way because I didn't want to overfit the limitations of the Rust AVR compiler at the time. And then none of this compiled. Okay, so switches or matches didn't, a lot of this didn't work. But I pushed through, and instead of changing my code to suit the limitations, I started fixing the LLVM backend for AVR, and then other people saw that, okay, this is going somewhere, so we made stone soup, right? Everyone contributed something, and then we got it over the line, and then I was able to compile it. So the way this works is that this is a standalone library. So it has no AVR specific stuff, but it also doesn't have anything that would not work on AVR. So that's why it's an OSTD library. And then that was super useful while I was developing it, because then I could have another package which uses SDL to implement a normal front desktop computer front end, right? So this depends on, so chip 8 is the name of the thing, and because it's written in Rust, and it's for AVR, so lots of R's, so I decided to call it chirp 8. And so chirp 8 engine is just the engine. And chirp 8 SDL has, of course this is not going to be no STD, right? It uses SDL too. It's going to pop up a window, draw into it, and read keyboard input and all that stuff. But it doesn't matter because it's a separate package. So if I run this and I pass it some chip 8 game, then this now runs like this is a memory game, like match 2 or whatever it's called, right? Like you get 8. So this links to the OSTD cargo package to implement the actual VM, and all the peripheral access is virtualized by having a trait for the things that need to happen outside the VM, right? So for example, you have read RAM and write RAM. So this is externalized because on the real AVR version, I wanted to make sure that I would have an easy time doing this by the communication with the external memory, like the serial RAM, right? And then you have a way of drawing on the screen, scanning heroes, and so on. So this is the trait that you have to implement to make your own chirp 8 front end. So the SDL version implements it in some non-interesting ways, because basically at that point this can just be the drawing on an SDL screen. This just makes a 4K array, right? And then we index into that, or maybe it's called a vector, right? I'm not up to date on my Rust. I think it's a vector, right? Yeah. So yeah, but then comes the interesting bit, which is the AVR version of this. So this one again links to chirp 8 engine, but also uses So this is not the 2017 version. This is the new version. This is 2024 version. Lots of improvements have happened since then. There is now very nice Arduino AVR libraries for accessing peripherals and everything. So this